Greetings and welcome to the second installment of the Balsa wood copper battery series. Welcome. So it might make more sense if you watch the first part. Then again, it might not. I mean, I don't really understand it myself, but I thought it was appropriate, you know, since it just like cuts off and then I'm doing something different, to kind of give a little bit of context before we get going. So how did this all come about? So let's just start at the beginning. I wanted to make a battery, and let's consider the idea of a traditional battery, a voltaic pile. And what happens? So you have two different materials, generally metals, and they like electrons a differing amount. One is happy to give up electrons, one is happy to take electrons. If you have those two dissimilar metals in a solution where there's a lot of ions, some of the ions break off of one and go to the other, and then negative ions break off the other, and then the charge imbalance gets replaced by your solution, your electrolyte solution, and the process continues and the plates dissolve. So there's two redox reactions. There's an oxidation reaction going on one side and a reduction reaction going on the other plate. And there's a voltage that flows based off of those two redox reactions. Oops. Within that category of batteries, you can have one, I think they, what do they call them, like primary cells, where it's really hard to reverse things. And then you can have another, rechargeable cells, where if you now put a voltage higher than the voltage established through the redox reactions, you'll reverse the reaction. And so those are rechargeable batteries. And so those you can just keep going with it. It discharges and then you can recharge it, discharges and recharge it. So that's what I was looking to do. However, as I was working on it and I was trying to get a good kind of, you know, consistent reading, and I was having some trouble doing that, I finally got to the point where I had two identical metals across an insulator and I was able to get a voltage out. And I was thinking, well, that's really weird. That's not supposed to happen, and that can't be electrochemical. That can't be redox reactions because the two materials are identical. So that voltage relates to either piezoelectricity, and these are all, you know, well documented, accepted things. I'm not just, you know, this is brand new. I mean, these are things that have been seen and documented before. So piezoelectricity, where when you put a mechanical stress on something, it generates a voltage, and the classic material for that is Rochelle salt. The other thing that can happen is what's called ferroelectricity, where if a material is exposed to a voltage, or if it's just sitting there, sometimes depends on, you know, how it just has a spontaneous voltage. It's just sitting there with a voltage. And again, you see that with piezoelectrics. You see that with Rochelle salt, and you see that with quartz and other things. Now, I will say the effect is rather subtle. You know, you're talking about millivolts, and if you're lucky, you can see microamps. So it's not like, you know, I'm going to power my house with it. And obviously, it has to be somewhat subtle because, you know, if lightning struck a tree, it's not like you go there 2 days later and it's got 200 volts in it and you get shocked. So it's a subtle thing, but it's there just to kind of back up there. I'm seeing piezoelectricity in wood. They don't seem to be terribly ferroelectric, but they're piezoelectric. So the second part of the video looks a bit more at just two identical metals and how it's doing in terms of just having a voltage sitting there. And then also, how does it play with the traditional voltaic pile? And when you start doing that, I'm realizing I'm just running right into the arena of the crystal batteries, because you know, a traditional voltaic pile copper zinc, or if you used silver oxide zinc, that would be the rechargeable battery that they used on the Apollo moonshots. So what happens if your dielectric, your insulator, is piezoelectric and or ferroelectric? And so you could think of a situation like if wood has some piezoelectricity, if you just had like paper spacers and you mash it down, you might get more amps out. So what's interesting in this part of the video that I'll show is, again, with the two similar metals, it's very, very subtle. You know, it's like, you know, you eventually maybe get it where, you know, I'm pretty sure I'm seeing, you know, 2 microamps, and then if I press on it, it's 3 microamps out. Then you put the same thing with 2 dissimilar metals, and it's just sitting there putting out a milliamp, say, because of the redox reactions. You press on it, and it's putting out 1.5 or 2 milliamps. So like 1,000-fold increase as compared to when they weren't dissimilar metals, when they were identical metals. And then the question becomes, is that extra half milliamp or milliamp, is that all from the piezo or ferroelectricity? And I don't know, but I mean, I suppose you could try to you know, make up a story like, well, it's getting better contact with the ions in solution or something. I mean, that doesn't make a lot of sense to me. I mean, maybe, but it seems kind of doubtful. I mean, you have like, say, if it's balsa wood, it's already really saturated. So I don't know. If that's not it, and that's about the best I can come up with, then it is from piezoelectricity, ferroelectricity, and it plays really nice with a traditional voltaic pile. You know, again, it's like a 50% increase in your amperage, but instead of going from a microamp to 1.5 microamps, you're going from a milliamp to 1.5 milliamps, which is pretty cool. I suppose the only way to really get to the bottom of that would be to just leave the things in solution until the galvanic corrosion dissolves the plates, and try it once where they're not stressed and once where they're pressed together, and measure your milliamp hours out. It'll probably take a long time. I don't know if I'll do that, but I mean, you could get to the answer. It's just, how difficult would it be? But even if it weren't from ferroelectricity and piezoelectricity, you still, if you mash the battery together, it's like twice as good. So, I mean, what's not to like about that? And if it's coming from ferroelectricity and piezoelectricity, then that would be really neat. Especially if you had, like, say, 2 rechargeable voltaic piles and like a Joule thief circuit or something like that. Be kind of interesting. So there's like a heck of a lot more to do with this. I mean, where I'm going next is I'm going to go to sand. I think I talked about that at the end. I'm actually really excited about that. Is silicon dioxide quartz sand is piezoelectric. I'm fairly certain it's also ferroelectric, and so you could use that as your insulator. And the nice thing about that, unlike Rochelle salt, which dissolves pretty quickly in water, I've looked at it, the quartz isn't going to care. It doesn't care if it's in a strong base. It doesn't care about a strong acid. It's just going to sit there, and you can really mash on it. Unlike, again, the quartz, the Rochelle salt crystals, and it's not going to care about that either. So that's on the weird branch of this. That's where I'm going, is to get some sand and see what I can do. On the traditional branch, I'm just going to be going back to trying to do something along the lines of a silver oxide zinc battery, and like one more one more thing angle I'm trying to go where it's still like in the normal lane instead of this weird lane. But the silver would get kind of expensive. And then what about electroplated gold on copper? And that would probably be less expensive than silver. And would it behave like it's seeing gold or like it's seeing copper? And I would think it behave like it's seeing gold because that's what the surface is on the surface. And gold's both more electronegative. There'd be a greater electronegativity difference. And it would actually be gold I think is the best conductor. Yeah, it's better than silver. It's better than copper. So that's where that should finally end up. But these things will take a long time. That's what I love about it. So the first thing is going to be to get some sand and just keep trying to get the lay of the land here of what's going on with some of the weird path. Let me stop here because I'll just talk all day. But this is what I'm showing in part 2, is just that it seems to play well with a traditional voltaic pile. Okay, so if we go back to when that was like 0.03 volts or whatever, charging the cap, is that free energy? I don't know. I'm not quite prepared to call it that yet, because we hit it with 5,000 volts, and so if this reverted to zero over say 2 days instead of like 2 minutes, as you would see with cap rebound if it's shorted, then you might not get as much. I mean, you'd have to fill this an awful lot of times before you had enough to generate a 5,000 volt spark to set the thing. That said, electrets, the beeswax carnauba electrets, they just sit there indefinitely. And what I never realized is that you can actually get current out of it. I know it's silly, but you hear these things and you just have mental blocks. I thought it was just like this disembodied electric field, like a whole new physics that you just make up in your mind to not accept things. But yeah, you can get electricity. That thing's just permanent. It's like a magnet. How long does a magnet stay magnetized? 500 years, if it doesn't go above the Curie temperature. So I'm not entirely certain that this is going to behave exactly like an electret, but if it were, that would be free energy. So, can you bear just like 2 more experiments? So what I'm going to do now is I'm going to do 2 things. Let's start to go back towards a conventional voltaic pile. And so we'll have a plate of copper and a plate of zinc. And as I said, if the plate were silver and you had zinc and you had a little zinc oxide and NaOH as your electrolyte, that was good enough for the Apollo mission, good enough for me. So I'll probably use copper, but who knows. Let's go back to that. And the point I want to drive home here is that the piezoelectric effect is in a real sense magnified once it can like source more ions or something. I don't know. But whereas when you have these non-dissimilar metals, it's just a tiny thing. When you have the dissimilar metals and it's under load, it'll put out 2-3 times as much amps once you start to press on it. So now we got a new sheet of copper, a sheet of zinc. I gotta sand that, and 2 new pieces of balsa wood. So one of these will go in. This is apple cider vinegar, which is a fairly weak acid, and then I dumped a bunch of sodium hydroxide in here. So that's going to be a strong base. So kaboom. It goes there, and I don't need it except for it's not gonna I gotta weight it down. Boom. And let those get saturated, and then I'll sprinkle a little Rochelle salt crystal on there, and I'll sand this, and then I'll show you what it does like this. So again, Rochelle salt isn't the way to go because it's too soluble in water. But I know the way to go, but I think I can get away with it for this experiment. So this isn't bad. we're sitting at 0.845 volts, 0.851 is trying to climb a little bit. And that, 99% of that, because I haven't hit it with 5,000 volts or anything, 99% of that is electrochemical. So what I want to do now is I'm going to load it across 100 ohms. Okay, before I even do that, this is the thing that I'm having trouble figuring out what it ever is going to do. So it's got the acid there. I'm just going to press on it, to do the piezoelectric, and it's working against us. Then let it go, and it'll want to snap back. I had thought that it was, so that's working against us right now. But let's go ahead and load it. It's just sitting here like this right now. We're going to load it across even just 100 ohms. So 0.76. So it's at like 65 millivolts, still kind of dropping. So that would be, what would that be? 63 divided by 0.63 milliamps is what we're getting out there. Now, if I press on it, what does it do now? Yeah, so even though it was driving the voltage down before, look at how much better the amps do. So this is, there's like, it's where no man has gone before. Actually, I'm sure a lot of people have done all this, but I don't know why it does that when it was. I mean, it was loaded before across just a 1 mega ohm resistor in here. Press on it and it goes down. Now it's across 100, and instead of getting out, you're getting out, almost 50% more amps. So let's blast it with 5,000 volts just because we can. I'm not even positive. I know that's going to be your negative electrochemically. Maybe that's what you want to blast it with the positive voltage. I don't know. It's all new to me, but let's try it this way. Well, it looks the same. Let me see what happens when we load it. It's better loaded, right? I think it was around like 60. Maybe it's just taking its time to get there. Let me press on it and see if it behaves the same. It's better. So that's like 1 milliamp. Last thing is a strong base. So now we have a strong base. As I said, this is what I'd like to go with because this starts to get really similar to what they used in the space program. They still use it. They still use it. So we see with the strong electrolyte basic solution, that's our resting voltage across the 1 mega ohm in the meter. Now if I press on it now, again, I have no idea, is it going to go down or up? It goes down again. It's not what I understand. I'd like if it would go up. Darn. So you can think about what would happen if it would go up. Actually, it's going up a little bit, isn't it? No, it's going down. So let's load it. And see again with it's going down over the 100 ohms there, but it'll settle out better than with the weak acid. It'll probably settle down around like 150, but what happens if I press on it? So that's, it still wants to go down, but it certainly changed it. So now you're getting maybe 3 milliamps out of a square inch. And again, this battery isn't charged. If you put zinc oxide in this solution, I'm pretty sure that's all that they did. And then you have a rechargeable battery. So, I mean, this is just its resting thing that it does because of the electronegativity difference. But you can see how much it changes. And if only when you pressed it, you could, yeah, that's beautiful. I mean, you're getting out, again, like 50% more amps. If only you could get the voltage to be higher than the electronegativity voltage difference here, then the thing would just trickle charge itself until you wanted to use it. So last thing, I'm going to zap it with a spark. I won't show that again. I've shown that enough. And then let's see what it does. Okay, after zapping it, that's at 0.989. I think that's a little higher. I can't remember. I'll have to see when I look at the video. If I press on it, just across the voltmeter, no, it's still going down. Let's load it. 100 ohm load. Is that better? We'll have to wait to see. You know, I think it's a little bit better. That's where it, you know, it's not going down real fast there at that. Now let's press on it. Maybe it's the same. Yeah. Maybe a little better. I think we're still in the same spot. Later off camera, I'm going to try zapping the negative. Maybe that's what you're supposed to do. I don't know. Okay, so just to recap and summarize and wrap this up. There is piezoelectricity in wood and other materials, and you can see that it plays nice with voltaic piles. So, I mean, that's just sitting there, and then I press on it, and it'll settle down at about 50% more amps out than we started with. So when I had the two identical plates, and we also saw the voltage, I mean, is that free energy? If it's, you know, to the extent that it's an electrode, I would say yeah. If it slowly goes down like a cap rebound that just lasts for a day or two, then you might lose more just charging it with 5,000 volts than you did putting in. But I think it's like an electret, and I suspect it's free energy. It's sort of, I mean, you know, you have there's no such thing as a perpetual motion machine, and the patent office will like throw it out if you say there's a perpetual motion machine. It's like Newton's laws of motion. An object in motion, it comes to rest. No, an object in motion stays in motion until acted upon by an external force. What does the external force do? It puts it off into a new vector. The motion isn't lost. All of creation is a perpetual motion event. So there's a certain lack of scientific rigor there, you know, especially if they try to like involve Newton in this. I mean, Newton said it correctly. An object in motion stays in motion. Perpetual motion. So it's not that much of a stretch when you have things like electrodes where they say that the electric field just stays there, that's perpetual current flow. However, you know, it is minuscule. I just thought of it as like, you know, this I don't know, you know, ephemeral, you know, voltage field that you could never do anything with. But you can see that you can get, as we were showing, you can get power out. So that part likely, you know, persists. I don't think it would be like enough to charge a cell phone battery or something like this. But then the question starts to become, all right, since it plays well with voltaic piles, you know, how do you engineer for that? And there are people that have done a lot with this. You know, I mean, you go look up crystal batteries. They have all these elaborate,
recipes, and they seem to do pretty darn well with it. I think the majority coming out, because you put in the water, and so that's going to be electrochemical, going back to Faraday. But there'll be a portion of it, small portion, that will be ferroelectricity, with the thing just having a resting voltage. What I never see anyone talk about, and I know, I was going to cuss there. I'm terrible with that. I know very well. I don't know for certain, but I know very well. Bedini and Hutchinson, they knew this. That just nobody ever says it. And so, how do you engineer for it? What's important is the piezoelectricity and the ferroelectricity. So, you want to zap it with 5,000 volts, or you want to put pressure on it. I remember there was on the a forum Bedini contributed to, and they were showing something like this, and I said, well, like press on it or something. It's like a couple days later, Bedini posted a picture of a hydraulic press that he was using. So they know all that. They knew all this. This has been known a long time. T. Townsend Brown knew all this. It's just a matter of, can you engineer for it? And when you're done engineering, is it something that belongs as a novelty in a toy store, or is it something you can charge a cell phone or a computer with? I don't know. So this is sort of going to branch into two branches now. I mean, one is I'm still going to go back and try to repeat basically the Apollo battery, and see if I can do that and have a good rechargeable battery like that. I just thought it was cool. I mean, I wasn't looking like for free energy or anything like that. It just came up and like slapped me in the face. And then the second is, since these things play well together, well, let's see if we can add some piezoelectricity and perhaps some ferroelectricity. The wood's somewhat piezoelectric. It's never talked about as piezoelectric, but it's somewhat. But there should be things that are more piezoelectric. They're generally things with crystals. What's the thing that's all the rage? Perovskite or something, after the Russian person that found it, and they use it in solar cells. That's ferroelectric, piezoelectric. The other one is silicon dioxide, quartz. So there's this very rare and special material, special kind of quartz that you could use. What's the name for it? It's this sand. I think that's what they call it, sand. Very hard to find, especially if you're not at a beach. So, but the more I think about it, use some freaking sand. That's going to be quartz crystals, and it's going to be, that it's piezoelectric and it's ferroelectric, and it's not going to give a darn. The problem with the Rochelle salt crystals, once they get some water in them, they start dissolving. The sand's not going to give a darn if it's in a strong base or a strong acid. It's just going to sit there. So there's a park. I'm not at the beach. There's a park, nice little bike ride away. And I know from walking around there that on the shore of the stream, there's a sandy shore. So that's going to be a little day trip. And what it seemed like from here is, once you had it set up as a voltaic pile, the big difference was the pressure. Much more so than if you hit it with a high voltage beforehand to try to condition it. So the sand will work great for that, and put in some sodium hydroxide, put in some zinc oxide. You have a rechargeable battery, which if you squeeze it down, should put out more, at least like 50% more amps. And this is with wood as the piezoelectric. I mean, what's sand gonna do? So people may watch this and, this is so stupid. Go pound sand. Now I can be like, hey, that's a great idea. That's exactly what I was planning. That'll be the next video. So stay tuned, you all, and God bless. Stay healthy. I really appreciate the encouragement and the comments. Thanks. It really does mean a lot to me. I don't know if I'll have time to get back to everyone, but thanks so much. This is stuff I'd be doing anyways, and it becomes 10 times more fun kind of sharing it. And if people say, hey, that's kind of interesting, then that's nice. So until next time, bye-bye.